Okie dokie. Now we're going to solve trig equations. Good news, they're just like solving algebraic equations. Bad news, instead of simple variables, you have trig functions. But the news isn't so bad because we kind of know what to do with them already. So let's just jump right into an example. We want to solve the equation 5 cos x equals 3 cos x plus root 3. So if we think of this sort of algebraically, we notice that we have 5 cos x's on this side and 3 cos x's on this side. If I just subtract 3 cos x from both sides, then I can combine them. 5 cos x's, take away 3 cos x's, just leaves me with 2 cos x's. And that equals root 3. Now, I'm trying to get cos x alone because then I can use an inverse function to determine which angle I'm talking about. So if I divide both sides by 2, I get the cosine of x equals root 3 over 2. And now solving for x is just a matter of figuring out which cosine, which angle of x gives us a cosine of root 3 over 2. And of course, let me go ahead and write it up. Cos inverse root 3 over 2 equals x, or let's put x on this side. X equals the inverse cosine of root 3 over 2 at pi over 6. Now, we've gotten our answer, sort of. We've gotten an indication of where all of the possible solutions might lie, because remember, when we're talking about reference angles, there are actually 4 on the first cycle, and then there are infinitely many whether you go backward or forward or loop around and around and around. But if we can get hold of where they exist on the unit circle, the first time around the unit circle, then we can just add multiples to complete our solution. So let's look. We want root 3 over 2 to be positive, and we're talking about the cosine function. So all students take calculus. Positive in the first quadrant, all trig functions. Only sine functions are positive in the second quadrant, and only tangent functions are positive in the third quadrant. So we're actually looking at the angles pi over 6 and minus pi over 6. And then we have to take into account all the times around pi over 6 plus 2n plus 2 pi plus 4 pi plus 5 pi, all the way around until infinity. So we write that by saying, therefore, x equals pi over 6 plus 2n pi, that's 2 times pi around, n times, or I guess I should say and, I'm not going to use a negative angle. I'm just going to say this is 11 pi over 6 plus 2n pi. And then I just have to identify what n is. N is an integer. Or probably better said than just n is an integer, saying that n either equals the set of all integers. This notation is set notation. Or I can say n is an element of the set of integers. So that's just a notation. Either one works, or it's technically okay if you say n equals z, just not specifically correct. So that was a darn good time. Let's do another one. This one, the first one we didn't have to use an identity. This one I suspect we will, just looking at it. Tan squared, or 3 times tan squared x minus 4 equals negative 3. So let's go ahead and get the tan squared x alone, just using algebraic steps. So I'm going to add 4 to both sides, and then I'm going to divide by 3. So I get tan squared of x equals negative 3 plus 4 is 1, divided by 3, 1/3. Well, now that I see this a little bit reduced, I can tell that, in fact, I'm not going to have to use an identity, because if I take the square root of both sides, I get tan x equals plus or minus the square root of 1/3, which equals plus and minus root 3 over 3. or I think probably better to write all the steps. So this would be 1 over root 3 plus or minus, and then root 3 over 3. And the reason for that is I use the left-hand rule to determine which angle this is. If you've memorized values, then this would work fine, but I use the left-hand rule. So when I hold down my ring finger and turn my hand upside down or backward to make the tangent function, I have one finger on top, which would be the same as, so we're looking at, I don't know if I can draw this. That's my pinky finger. Then I have put my ring finger down, and then I have 2 fingers and a thumb down. So in this case, I would be looking at, remember what's in the palm of my hand is the square root of something over 2. And for tangent, I'm going to have whatever the sine function is and whatever the cosine function is, so the 2's cancel. So what I care about is the top value giving me 1, and it would take a 1 inside the radical, and the bottom value giving me root 3. So that's 1 over root 3 happens when my ring finger is down. If I switch my hand back over, I can see that that's a pi over 6 or multiples of pi over 6. So I'm just going to make a little note here that I'm talking about pi over 6 degrees before I evaluate where they are. So this blue part, those of you guys who know the left-hand rule and use it with me in class, understand what I just did. The rest of you are thinking, what the heck is that? Oh, well, I assume you already have memorized these and you just knew right off the bat that we were talking about multiples of pi over 6 or reference angles of pi over 6. So now let's sketch out our reference angles for pi over 6, our possible possibilities. So we're looking for the tan inverse, or the inverse tan of root 3 over 3 equals, and we want the positive and the negative values. And so we know that the inverse tan of pi over 3 is at pi over 6, okay? Then we just have to figure out which ones. Well, we're looking for positive and negative, which means we're talking about all of them. So I probably didn't have to sketch them all out, but pi over 6 at 5 pi over 6, 7 pi over 6, and 11 pi over 6. All of these angles would either be a positive or a negative pi over 6 or value of root 3 over 3. So how do I say this? Therefore, x equals, well, pi over 6 in the first quadrant, and then I can put this into the same statement, right? Plus pi plus pi plus pi plus pi plus pi times n, or technically we actually write that n pi. And I've covered these two now. Let's look over here. This would be 5 pi over 6. And I want to get this one caught up in there. Let's see. So we're looking at 5 pi over 6 plus pi would give me the 11 pi over 6, and multiples of each if I add n times pi. And then again, just saying that n is an integer. All right, so another example. We want to solve or find the value of x for the equation, the trigonometric equation, 2 sine x cos x equals square root root 3 sine x. And this time we're going to limit it to the interval 0 to 2 pi. And all that does is put us exactly on the unit circle, so we don't have to include the n pi part, right? So we're only going to get whatever the initial angle is on the unit circle, and then we're not going to look for multiples beyond 2 pi. That's all that does. It makes it a little bit easier when we're reporting our work, and it doesn't give us or take away any new understanding. So in this case, we're looking again at this as though it's a polynomial or a algebraic equation rather than a trigonometric equation. Now you might be tempted to divide both sides by sign, which means that these signs would disappear. But just like dealing with algebraic equations, you can't just disappear a value because you can. Like, it's possible to divide both sides by sign, but we're actually looking for thetas, for angles that are of sine theta. That's part of the equation, and so we can't really just disappear that. So just like in algebra, we're going to subtract root 3 sine x. So I have 2 sine x cos x minus root 3 sine x equals 0. So remember, solving in algebraic expressions involving polynomials, we often want to just get everything on one side equal to 0 and then do some factoring. And so the same thing here, we're going to factor that sine x out. So sine x times 2 cos x minus root 3 equals 0. And so now what I really have is just some factors that I can solve x by with using the zero product property. We're looking for the case where sine x equals 0, and we're looking for the case where 2 cos x minus root 3 equals 0. Well, sine x equals 0, that's easy. We know that sine x equals 0 whenever x or theta is 0, pi, and 2 pi, and multiples of those. And since we're looking on the interval not, or including 0, but not including 2 pi, we're going to say at x equals 0 and pi. The other side, we want to do a little bit more solving, so we're going to add root 3 to both sides and then divide by 2. So cos x equals root 3 over 2, and we're talking about cosine of x, which means I want 3 numbers above. I'm going to do the left-hand rule again. So I want 3 above. So I've got my thumb, my pointer finger, my middle finger, the ring finger is down, now my pinky, and so what I have is root 3 over, well, 2, because we're not worried. This is the cosine region of the left-hand rule, and this is the sine region. And since we're looking for cosine, I know that I'm talking about a 30-degree or pi over 6 angle. So cosine equals, or x equals pi over 6 and multiples of pi over 6, or excuse me, and reference angles of pi over 6 wherever cosine is positive. So all students take calculus, so pi over 6 and at 11 pi over 6. Therefore, my final answer, x equals 0, pi over 6, pi, and 11 pi over 6. So that was an equation that involved factoring by monomial extraction. This time, let's use something that has a little bit more complicated factoring. So 2 sine squared x plus sine x minus 1 equals 0. So this is just a simple factoring number, but sometimes it's hard to see when you're dealing with a trig function, so we can turn it into a polynomial or just an algebraic expression. Suppose we let sine x equal a. Now I can write it as 2a squared plus a minus 1 equals 0. This is just a magic numbers. 2 times negative 1 is negative 2. Two numbers that multiply to give me negative 2 but add to give me a positive 1 would be 2 and negative 1. Divide the 2 back out and then decide at this point, do I want the solution or do I want the factors? And I want the factors because that's what I'm doing here is factoring. So this solution would lead to the factor x plus 1. And this solution gives us the factor 2x minus 1. Now, O equals 0. I'm not going to zero product property it here. I'm going to take it back over here and make my substitution. You may be able to see that up here and not have to do the substitution and work with your factorings in algebraic expressions. Whatever works for you is great for me, just as long as you can get the factoring done. So in this case, we're looking at putting the sine x. Oh, look what I did. Hang on, let me go tidy this up a little bit. So we're used to using x. So this is a minus 1, and then, or a plus 1, and then this is 2a minus 1. All right, now let me make my substitution. So this expression, this trigonometric expression factored, would be sine x minus 1, plus 1, times 2 sine x minus 1. And that equals 0. Since I have factors and equal to 0, I can use the zero product property. So I have sine x plus 1 equals 0, and 2 sine x minus 1 equals 0. Sine x equals negative 1, and sine x equals plus 1 divided by 2, 1/2. Now we just have to find the angles of x that make each of these conditions true, that satisfy both conditions. So first let's look at sine x equals negative 1. There's only one place where that's true, and that's at x equals 3 pi over 2. And on the other side, only one place where the sine, or excuse me, there are two places where the sine of x equals 1/2. There's the position for the first quadrant where we're looking at pi over 6, and then all students. So in the second quadrant, we're looking at 5 pi over 6. And in this case, I didn't write it down, but this is part of the same example where we're holding the condition to include 0 and all angles up to, but not including 2 pi. All right, so we don't have to write the n pi notation this time. So we're looking for this case, sine x equals negative 1 at x equals 3 pi over 2. And in the second case, sine x equals equals positive 1/2 at x equals pi over 6 and 5 pi over 6. And then we just want to make a final neat and tidy, pull it all together solution saying that x equals, and let's work in order, pi over 6, 5 pi over 6, and 3 pi over 2. And so these are the solutions to this equation. These are the angles, 3 angles make this sentence or this trigonometric equation true. And that's probably enough for this lesson. Next lesson, we'll look at a few more. This time we just looked at solving trigonometric equations as though they're algebraic equations, right? But instead of variables, you have trig functions. And you can either solve directly, getting to some value and use the inverse function or the unit circle to find the value. Again, here, same thing. I had to do a little bit of algebraic manipulation to get there rather than getting there directly. And then finally, a couple examples where I had to use factoring, another algebraic manipulation. And that's that.